Hello again. Tonight we're going to be talking about something that I went looking for in the Broward Astronomy log of videos that we've done, and I didn't see that had done it before, but it's a topic that I've done research on. It all comes down to one particular isotope of one particular element. It's been found on Earth and kind of explained away as geological, and now they found it even in greater concentrations on Mars, where the geology works a bit different, and they're trying to find a reason why it would be that. So, like I said, this has been on my mind previously. Haven't done a Broward astronomy presentation on this. I've watched YouTube videos about there being the potential for far deeper history of sentient beings on this planet. Maybe humans, maybe not. But how would you detect them? And I've watched the videos on the Science Channel or Discovery that explain how things that we create in our environment, our technology, our infrastructure, you start going out tens of thousands to hundreds of thousands of years to millions of years, and a lot of those things that we create just wouldn't stand the test of time. And then you throw in ice ages and sea level movements up and down and covering and receding land masses and plate tectonics, and it, it's not going to survive. The things that we have found about history and prior existence is, we found mummified bodies and fossilized bones of ourselves and dinosaurs and footsteps into fossilized hardened rock. And if you look at them, they only go back tens of thousands of years. The dinosaurs go back a few million years, maybe 200 million years, but nothing before that. We just make the presumption that there was no sophisticated life on the planet prior to that. Well, yeah, okay. But if things did exist and they did get oxidized or eroded or things like that, what would we see? Well, let's say there was a tunnel for vehicles that you made underground, and through tectonic action, it submerged further, and then it got compressed and broken apart into sections. Maybe you could see that if you were looking for it. But if it got compressed down to the point where it was just a gap in strata and not a tube, then we probably wouldn't even detect that. And not even the durable stuff that we create, like iron beams in buildings or stainless steel rocket bodies or titanium aircraft, military aircraft. Once you start throwing in all of these agents and things get compressed and turned over due to tectonic plate activity, they just wind up being veins of materials in strata, a literal reset based upon geologic change. What would remain, and we've actually seen this in Jack Hill's zircons, is what's the oldest material on the planet, and it's zircon crystals that are close to 4 billion years old. That's the biggest structural thing that we can find. Once you get out to a billion plus, there's no material that survives at all. But there is one more material that doesn't have a crystalline structure to it, and it's a particular form of a radioactive isotope. But what these would be is byproducts or leftovers from nuclear weapons testing, nuclear fission processing facilities, particle research, fission-based power generation plants. And it's not the plants themselves, none of the electronics, none of the metals and stuff like that, nor the uranium itself would be left. What would be left would be the isotope byproducts of it. So I was watching videos, as I do each week, and I found one that was similar isotope discoveries on Mars, not on Earth. Sure, there can be wind and water erosion if you go back a couple of million years, but long-standing plate tectonics like there is on Earth, not so much. Even though it has volcanoes, plate tectonics is not as aggressive on Mars. So the particular material is the element xenon. It's the heaviest of the noble gases. It's stable. It's extremely inert, yet under a synthetic processing, it can actually form compounds. Obvious when it's something called xenon hexafluoride. Doesn't form in nature. You have to synthesize it. An isotope is an atom of material with the correct number of protons, but a very much larger number of neutrons. For example, xenon has 54 protons, and in a non-isotopic, non-radioactive form, it has 54 neutrons. But the more and more it has neutrons, the more radioactive it's going to be. And there are sweet spots where if you get the right number of neutrons, then the material will take longer and longer to decay. And for example, there are other elements like uranium and plutonium that their decay produces useful byproducts like heat or weapons or things like that. But when they decay, they can produce other elements. So their big isotope elements will break apart and produce smaller ones. So, for example, there's lots of them that they find in particle accelerators, and those very heavy isotopes don't last even fractions of a second. What they call a short-lived one is francium-223, which lasts for minutes before it goes through its half-life and starts decaying. Then one called short-lived is radon-222, which lasts for a few days. Then there are longer-lived ones, the ones that we think of as being highly radioactive, and we have to isolate them, and so they could last hundreds of years. So we put those underground. But the ones that can be very long-lived, taking hundreds of thousands to even millions of years, they're just going to be radioactive isotopes breaking apart into other elements that are also isotopes for a long time. But the longest lived one that I found is Xenon 134. It has a half-life of 10 to the 22nd years. So if ever there's any Xenon 134 produced, it's essentially going to last forever, 10 to the 22nd years. We're talking more than billions. So when you get above Xenon 129, they kind of no longer reference it as being a radioactive isotope. Like Xenon 134 is so long-lived that they just label it as being stable, even though it's got way too many neutrons. It's not going to anytime soon decompose into other elements. But Xenon 129 is very long-lived, recognized kind of as stable, but still an isotope. But it's detectable. It's not 10 to the 22 years. It's only, tens of millions of years. So when you find xenon that's ultra long-lived, how did it come into being since it's not a natural element? Well, it had to come into being as a result of the radioactive decay of another isotope. Xenon actually comes out of the longest lived xenon isotopes come out of the isotopic decay of a particular isotope of iodine, which comes as a result of either natural decay of uranium or synthesized and purified uranium, or even plutonium. You can get the iodine out. But the naturally occurring sources of this particular isotope of iodine that would produce the xenon should have not been around after the first million years of Earth's formation. So when Earth was first forming and you had this very hot ball of material that was compressing, there was radioactive iodine being produced. And as the Earth radioactively released a lot of that material, the amount of radioactive iodine that would be left to produce the very long-lived xenon would have not been sufficient to make the amount of radioactive xenon that we see. Anything that's shorter-lived xenon would essentially have, basically bled off into space from the surface of the Earth. So the only xenon we find at high half-life levels is below the surface. And there is a geologic process where you can take uranium and through water, moving through the uranium with certain elements in the water, you can actually make it produce a uranium that has a higher level of purity and so produces more radioactivity. It's not going to be producing the particular isotope of iodine needed to make the extremely long-lived xenon. It'll make short-lived xenon. So high concentrations of short-lived xenon can occur in natural fission under the ground. Or you can get the same effect through detonation of fission and fusion, which requires a fission ignition, weapons, or power plants, or particle research. But once you get out beyond millions of years, it's kind of hard to explain how geology could have produced these ultra long-lived xenon isotopes, whereas waste products of artificial processes would be the more common way of producing it. So when they discovered, well, the Mars Curiosity rover discovered these particular isotopes of xenon in the atmosphere of Mars, they had to explain, well, where did they come from? And they came up with this concept of cosmic rays in sufficient quantity penetrated the surface of Mars, entered into the regolith, the subsurface, and hit barium and bromine atoms and broke them apart into xenon and krypton. And somehow the missing step was there to take the xenon and krypton and come up with the radioactive isotopes of it. If you look at the numbers there, you'll see it's xenon 124 and xenon 126. But that's not the most longest lived of the xenon isotopes that they've detected. They just kind of conveniently left them out of the picture. You notice there's no iodine there. So where are they getting the long-lived xenon isotopes if there's no iodine? And if barium and bromine, when they break down due to cosmic radiation, won't be producing the ultra long-lived xenon? They just don't have an answer to that. But I would say that if sufficient cosmic radiation bombarded Mars, let's say 500 million plus to a billion years ago, that level of cosmic radiation would have sterilized the Earth. So if there was any early forms of life, single or multi-celled things on Earth, that level of cosmic radiation would have sterilized the planet. And we're here, so that didn't happen. So it's interesting to see how they're stretching to come up with a natural way where these very long-lived xenon isotopes could have formed naturally. So what they found was higher than expected concentrations of these long-lived isotopes on Earth, but then even higher levels on Mars. Hard to explain how they could have been naturally or geologically formed. We produce them as fissionable materials decay and reactors and particle accelerators and detonations of things. We have answers for how this could occur. So if let's say there was infrastructure that's now gone, there was life that's now gone, when could it have occurred? So I took the NASA Night Sky Network Earth Timeline presentation and I found a gap. After photosynthesis creates oxygen in the atmosphere, and before the evidence of multicellular organisms that sexually reproduce, there's this thing that is a gap between the two, between 1.5 and 2 billion years ago, that kind of nothing goes on because we have no records of what took place then. Cores and things like that don't go back that far. You're more than 1 billion years ago. You might have some crystals, but you don't have any infrastructure. You don't have any bones or skeletons or things like that going back that far. From what we understand, the days were only 20 hours long, so Earth was spinning faster, but the years were taking longer, so the Earth was taking longer to go around the sun. And there would be a window between 1.5 and 2 billion years ago of about 500 million years where life could have gotten a bootstrap, actually created something on par with what we have today, and then a catastrophic event occurred and it did a reset, and we have no record of it. So there is the possibility, there's a window where you could have at least what we have today and then go through a catastrophic reset and then start over again. And you'd have plenty of time to get to what we have today. So there's a window on Earth. Is there a window on Mars? Turns out, here's the Martian timeline, not from Night Sky Network, but associated with NASA. And there's a period of time called the Amazonian on Mars, where You have stabilized atmosphere and geology, far fewer meteorite impacts, non-trivial amounts of water, some volcanoes, some glacial activity, kind of like early Earth, but there were no extinction level events threatening any advanced life forms that wanted to form. And that would be between 1.5 and 2.5 billion years ago. And remember, it only took 250 million years to get from essentially nothing to where we are today. And that's, you've got a window there that's much, more than twice that size, and no evidence of what took place back then because it's all been essentially eroded away. So if you discover expected concentrations of xenon, but they're of rare isotopes that are very long lived, you might be able to explain some of those isotopes through geology, but the very long lived ones you can't explain without the presence of isotopes of iodine, which would have been gone about some period of time after the Earth was formed. But you can find xenon isotopes down in veins of fissioning uranium, naturally fissioning uranium. But that gets to be thinner and thinner. But if you suddenly discover that on Mars, and you discover even higher concentrations of these ultra long lived isotopes, and they're absent iodine, you need a much farther stretch to explain it as a natural process. So as the saying goes, extraordinary claims require extraordinary proof. I look at that and say, well, the claim that it was geologic is kind of stretching the extraordinary part in the absence of iodine and the fact that these ultra long lived isotopes are on Earth and are on Mars, and there's no iodine that would have created them. But they're long enough ago that all signs of any advanced civilization or biologic life forms would have gone. And there's no signs of any advanced technology on Mars, none that we found. But there are higher concentrations of xenon long-lived isotopes on Mars than there are on Earth. They can't come from uranium because there's only trace amounts of uranium on Mars. And the required level of cosmic rays in the absence of iodine would have sterilized the Earth, and we're here. So sometimes the simplest explanation is the correct one. The long-lived isotopes of xenon aren't naturally formed. I'm not postulating that they were. I'm just, saying here's what the data shows and asking questions. And I never mentioned Silurians. Oops. With links to all the material, including finding xenon in the atmosphere. Hey, I made a reference to a Night Sky Network presentation. Okay. Comments? Questions?
I'm thinking we think in terms of our own point of view,
Yes.
but I wonder what they would say, what the people of Mars would say to a Martian astronomer looking down at, let's say, Florida, saying that he thought he saw canals.
Well, I would say if they were more advanced than us back then, they would have looked down on Earth and went, Florida looks a little strange because back then, Florida, the bottom half of the peninsula, would have been dry. You wouldn't have Lake Okeechobee. You'd have essentially coral shoals. That's why there's so much coral rock beneath Florida. So, different views at different times. But as far as what they observe, I've got to give them the credit for having technology that's at least as good as what we have today, possibly better. And so they wouldn't come up with the fanciful canals on Mars kind of thing. They would more likely be saying, how come all we see is animal life? We don't see any higher species on this planet.
Yeah. Just us.
Yeah, because if we can today with our technology read a license plate from a satellite in Earth orbit, if we advance that technology 1 million years and we put that on Mars and then go back 500 million years and give them that technology, they could clearly see on Earth all of the flora and fauna. We were the creatures maybe in skins roaming around.
You wonder about other technology civilizations. They wouldn't have to actually go anywhere. They could see it from where they are.
Yes. Years ago, when I did a presentation on the original creation of astronomical telescopes and the Earth going around the sun as opposed to the sun going around the Earth, we've actually discovered that as a species 5 different times. We're in the 5th definition of that. I originally found that it was only 4, but then years later I found, oh, no, we actually have evidence going back even further that says we discovered that the Earth goes around the sun, the diameter of the Earth, the diameter of the sun, and then because of various sociological reasons, typically, that was lost knowledge. And then later on, somebody got smart and noticed it again. And it took place far before we ever invented the telescopes that would allow us to come up with the observational evidence of it. Yeah, given the number of times we've kind of been reset, and that's just reset of our space awareness technology, but the species itself, the human species itself, has gone through 4 complete resets, almost back to no animal life on the planet, and we've come up again. So imagine if instead of having 4 resets of our physical being and 5 resets of our technological advancement, what if we only had 1 or 2? How much farther along would we be? And if that's the case, yes, maybe we would be observing things from a distance rather than trying to go somewhere. One of these science fiction technologies in the Star Trek movies, not in the original series, was the ability to look at something from a distance and essentially pick up all the available photons and run them through an amplification process and have a high resolution digital image of something that's well beyond what you would think of as the ability to see with an optical telescope. I've often postulated that the only difference between 2 particles at 2 locations is not the particle type or the particle energy level, it's the location of it. And yeah, it moves around quite a bit, but the particles have, at a particular instance in time, a location. And if you can map a location from one place to another, then you never need to go anywhere. You can just observe it from a distance. Going deeper into the science fiction realm is the TARDIS of Doctor Who. If the TARDIS is really pulling itself out of 3-dimensional space, moving around through time and space, and then depositing itself in another place in time and space, it doesn't really need to do that. It just needs to open the doors to another place. So the machine itself can be massive, and all it needs is a door that allows you to say, I'm going to make the door opening show up in another place in time and space, and I open the doors and I walk out. I don't need to move the whole ship. Same thing, if you can observe from a distance, then maybe you don't need to go there. Just what you said.
Yeah.
Maybe we'll get there someday. But first we have to advance our technology, and we have to spend the money to advance our technology. And we're in one of those sociologic periods where we're not going to be spending as much money advancing the science and technology.
I was taught that an advancement of intelligence was that one animal could tell another animal something that's happening beyond what he could see. So the second animal says, "Oh, I believe you. You're telling me there's something over there."
Yes.
And so the same thing. We feel that we have to go somewhere all the time. We have to go see it
Hey,
ourselves.
adventure is one of our key factors for broadening our existence. I think it's more a matter of, I'm feeling crowded here. Let me go someplace where there's more space, because
Like
usually that's why we would go somewhere, is I want to find things that I can get from over there that I can't get here, or this is really crowded and the society is oppressive. So I'm going to go someplace where there's room to breathe and room to grow. And maybe there's something better over the next hill.
room to swing a cat.
Yeah, yeah, room to swing a cat. Okay. Anything else before I stop recording? Hearing nothing.